谢谢。那边对方的助教那边还好吧？
对，就他有说他会跟我讲，
蛮清楚的啊，应该是蛮清楚的。
他是没有回应，应该是没有问题。
那个音符在上面看，好像他说的蛮清楚。
哦，是啊。
有效果不错，你这样换来换去，效果还是不错。
哦。
Okay, begin the second hour. If you have any questions, please raise your hand and ask. Yes, please.
Yeah, I'm having a little confusion here because we said X1 is
state.
State, which is displacement,
right.
And X2 is state, which is velocity. Now, does it mean because the state here inverse of mk,
right?
That stands for the stiffness, right, of the spring.
That's the stiffness, yes.
So does it mean the stiffness is related to the displacement only in that system?
For this measurement, yes. For the measurement, yes.
Just okay.
And because you use the acceleration measurement, you have m inverse k that related to your displacement. You have m inverse c that related to your velocities.
But is it just for the stiffness, that is the spring, and the damper alone?
Right. That's the if you have a spring only, then you don't have c term.
Okay. Yeah.
If you have a spring and despot, then you have two terms. You have one is related to your state, m inverse k, and you also have another term because of your c. That's related to your velocities. Yeah. So c only related to your velocities, yes, because you look at the equation of motion cx1 dot.
Yeah.
So you have velocities, then you have that you do have that term, you have c.
I got it now.
Okay. So k is, yes, you are right. K is only related to your displacement. C is only related to your velocities. And in physical meaning is the K will keep the energy conservative. Whenever you give the energy to the system, the K will keep it. They won't let it go. The C will let it go. C will take your energy out from the system. All right. So if you don't have a C, if you don't have a despot, then your system will keep moving. Will never end because the energy is still there. The C there for you to dissipate energy. The energy will dissipate by the C. Control is very simple. Means what? If you want to take energy out, you need to add a decimal. That's it, right? Control theory, just like that. Simple. Now, if you want to transform, you want to keep your energy, then you need a K. However, the point is, in any mechanical system, if you want to get energy from the system, then you have to have a K, just like your motorcycle. Why we have spring there? Because spring will take the energy from your system to spring itself in there. And then your despot will try to take out the energy from there. So the control is very simple. You need a displacement, you need a K, you need a C when you design a controller. All right. Understand? Yeah. Okay. All right. So that is That's what I see here. I tell you that the K spring will that's related to displacement only. The dense part related to velocity only. So C multiplied by velocities, C multiplied by the velocities, that's the term, is minus C x1 dot. K multiplied by displacement is minus K x1. All right. And again, or any mechanical system or civil engineering system is nothing but this the combination of a subset of these three, or the full set, or a subset of these three motions. And so if you have a very complicated mechanical system, that means you have many eigenvalues. That's it. And each eigenvalue has an imaginary term and also have a real term. Each eigenvalue, the imaginary term of each eigenvalues means the frequencies. All right. The real part of the eigenvalue of each eigenvalue means there's damping for that frequencies. Understand now? Very simple. So any mechanical system like that. So some system may have 10 eigenvalues. That means that system has 10 frequencies involved in it. Okay. So the last hour, I spent an hour, it took me an hour to explain to you the meaning of eigenvalues of a system. I didn't talk about eigenvectors yet, or eigenvectors, also very important, because that gives you the motion shape. You have a motion frequencies, you also have a motion shape. All right. Again, if you have any question, please ask. In the remote site, if you have any questions, just type. This is live stream video, just like TV broadcasting. It's live. So if you have any comment or any questions, write down there. We can see it. All right. We got realistic case. Ideal spring, like that, will keep our energies move all the time, damped frequencies. All right. In a real, in a realistic case, you don't really have an ideal spring. You do have some spring damp. Doesn't matter what kind of spring you have, you always got a little bit damping, but that may not be enough for the system. So if you have a spring and dense part, just like this, and this is really nothing but well, I didn't have. There's a website there somewhere that you can show you that what kind of motion you got there. But anyway, again, all the system is nothing but a combination of these three. All right. So I show you. I call realistic case. Now let us talk about Thun mass damper. So last week, I introduced you the application of Thun mass damper, right? The Thun mass damper is nothing but this. This is Thun mass damper, and their equation of motion is like this. Simple. This. The C, the 2 here, C2, K2, M2, those are the parameters you can tune. And then K1, M1, that's assume that's the system you have. Assume the system you don't have any damping. Well, that's not true in the real case, but I assume that your system don't have any damper. Just have a spring. In other words, your system got only the frequencies, only got the spring involved in it. All right, and so that's the typical Thun mass damper equation of motions. And to derive this is easy. It's very easy to derive this. which I will show you how to derive equation of motions maybe next week, whenever we talk about the dynamic modeling of a system. All right, and for this moment, just trust me, this is correct. And the first order equation of motions, if you look at this one, then you got a 4 equation. If you convert it from second order to first order, then you got a 4 first order equations. And by the way, this is only one way to convert from second order equation of motion to first order equation of motion. There are many other ways to do that. This is only one way. And this is only a very classical or conventional way to write from second order to first order equation of motions. But on the other hand, you can have all kind of different ways to do it. If you want, why you want to have a different way to do it, I don't know. But some people like to have a different way to do it. That's fine. So convert from second order to first order equations is not unique. Listen carefully. It's not unique. All right. So a matrix equation of motion. Look at this. And that's the matrix equation of motion for the tuned mass damper. All right, again, we assume here M1 come from the system, K1 come from the system, M2, C2, K2 are the parameters you can tune. Now, why you want to tune these parameters? For example, I give you an example. Now, if you work on a suspended bridge, okay. Now, if you have a team of soldiers walk on the bridge, then if you match it, what happens? It might excite the frequencies of the bridge, right? That means your matching steps happen to oscillate the bridge, right? Agree? You don't want to do that. So if you're a real good commander, they don't want to say match, right? They want to just walk randomly, right? So K2 here, the K2 here, the mission of the K2 here is what? The mission of K2 here is they try to move the energy from K1 to the K2. And that C2 to damp out. So when you choose K2, you got to be careful. Why? You want to choose the K2 such that your M2, K2, the frequencies close to the frequency of the system. Otherwise, they will oscillate. Agree? When they oscillate means your energy will transfer back and forth between the system and the damper, the tuned mass damper. All right? And if you don't transfer your energy from system to the damper, your damper won't do anything. Can't do anything. Agree? In other words, we have to have the motions of X2. If you don't have any motion of X2, the damping C2 cannot do anything. Think about it. If your K1 is very rigid, then what happens? You don't have any radiative motion between X1 and X2, right? Then if you don't have any radiative motion between X1 and X2, then you don't have any radiative velocities. Then your C2 cannot do anything. Because the C2 has to have X2 dot minus X1 dot. If X2 dot equal to X1 dot, C2 is doing nothing. Agree? We are talking about physics. We don't worry about the mathematics here. And you have to look at the physics of that law, every terms. Okay, now look at that. M2 x2 double dot equal to minus k2 x2 minus x1 minus c minus c2 x2 dot x1 dot minus c. Now, if x2 dot equal to x1 dot, c2 multiplied by 0, your c2 is doing nothing. Won't do any good. It won't dissipate energies. If x2 equal to x1, then the k2 is doing nothing. That's something you don't want to see that. When x2 equal to x1, if k is very large, what happens? x1 will be x2 very close to x1. Agree? If C1 is very large, the same thing. Then M1 and M2 just stick together. Do nothing. Agree? If we don't have, if K2 equals 0, then what happens? Think about that, right? The energy won't move from your system to that damper. I'm doing nothing too. So it cannot be, K cannot be too small, cannot be too large. I just tell you K cannot be too small and cannot be too large. The same thing, C2 cannot be too small and cannot be too large. C2 means your dissipation energy is very small. C2 very large means the X1 and X2 they stick together. Somewhere between means the best. Right? That's something we are looking for. Where? How? That's what we call tune mass damper. This is why you need to tune your mass damper. You have to tune your K2, you tune your C1, C2. Assume that M2 is giving. Well, in 101, you don't want to put too much mass on the top of 86th floor, right? So, M somewhat has to be large enough, but cannot be too large. Too small is don't do any good. Too large is going to damage your building. So there's some certain reasonable value of M2, of mass 2. As soon as you fix your M2, then you can tune your K2 and C2 to the frequencies. For that particular frequencies, you want to take the energy out. That's simple. So tune mass damper is the simplest way to do it. You can just base on that to earn your money. So that's what I call tune mass damper. We'll have a chapter just talk about tune mass damper. Here we don't really talk about that. And this is a TMD demo, and you can go to Core Mathematicals. There's a TMD demo that you can. There's a website there. You just go to that website. You can go there and you can tune the. They have a way to tune the damper and the K, the spring, and then you can see the differences. You go home and doing some exercise by yourself in your computer. It's free. The demo is free. You can just go to play for that, and that's the website. You can do it. All right. Let's look at the pendulum problem. The pendulum also is a a classical problem for the system. But that's a nonlinear second order equation of motion. A simple pendulum motions is this, like that, is a nonlinear equation. M d2 d squared theta divided by dt squared plus mz sine theta divided by L equal to 0 if you don't have any other force except gravity. You have only gravity force for this system, nothing else. Then that's the motion you have. So this is a nonlinear equations. Look carefully at that. It gives you the vector of the velocities v, and then accelerations. That show you the only the vector, and the length is the amplitude of your accelerations and velocities. So you can see that acceleration and velocity, they are not really the 180-degree difference. They are somewhat, there's some angles for those directions. If you look at this, by the way, you can go to Google search. There are a lot of pendulum motions. Some video you can see. All right, and that's just something that interesting. All right, okay. Let's look at the ODE. All right, and I will explain to you what we mean homogeneous ODE. You know that in the I think you already taught the engineering mathematics, and they talk about ODE, but I'm not talking about math here. I'm talking about some physics here. All right, homogeneous ODE. What do we homogeneous mean? All right, homogeneous. Homogeneous means the system. Homogeneous. Homogeneous. That means homogeneous ODE implies the system has no external force. Right? No external force. Right? In control theory, in what? Well, let me put this way. If the system no external force, then where the motion comes from? Anybody has any idea? If the system has only external force, how do I have a motion in there? Huh?
The weight of the body, the system.
Well, one, maybe you have an initial conditions. Right? The system you have initial, like a spring, you give them initial condition, pull it out, and let it go. All right? Then you have homogeneous solutions. Or you have external force applied to it, and then you release your external force. Then if the system has no damping, then they have a motion involved in there. Agree? Now, that in control theory we call transient. Response. The transient response means the system, before we apply any force, the system is moving. So we call it transient response. It's the same thing as homogeneous solutions. The homogeneous equation means we don't have any force in there. The homogeneous solutions, then we have this like this, for example, spring despot system. Then this is a homogeneous ODE for this very simple spring system. Then that's d square x divided by dt square plus 3 dx dt plus 2x equal to 0. If I don't give them any initial condition for these systems, we have no motions. Agree? For this system, if I don't give any initial conditions, how can I have a motion? Nothing. Well, we look at this system. Again, don't look at the don't look at a mathematical equation. It doesn't mean anything if you don't have any system to describe it. Okay, now you look at this system. This system again. This system, if I don't have any initial condition involved there, then this system really have no motion at all. In other words, to solve this equation of motion doesn't mean any good. Any homogeneous solution, you know that from your engineering mathematics. If all initial conditions are 0, the homogeneous solution are 0. That's right. Yes. Yes. So homogeneous solution only initial condition dependent. There's nothing to do with force. No, I don't have any force in here. Right? Agree? Are we in peace? Okay, good. All right, this is really the equation of motion that describing your motorcycle system, like that. Of course, not 3 or 2. That's something I just randomly giving. So, homogeneous solutions here in the engineering mathematics that just I call here the transient response for the system. All right, exponential functions. Then I'll look at exponential functions. Look at these exponential functions. You've look at it, depending on how many terms you have, n equal to 8, n equal to 1, n equal to 0. You get all kind of different curve. But when up to 7, about 8, then it close to real exact solutions. All right. Why I want to show you this exponential functions? Because homogeneous solutions always involve exponential functions. Does can anybody tell me why homogeneous solution always involve in the exponential function? Why? Why not something else? Huh? Why? Can you tell me why? Anybody? Why? Or is it mathematics because engineering mathematics textbooks tell you that? Right? You trust them? I don't. Well, let me tell you. As a matter of fact, As long of any differential equations got exact solutions. So somebody invent these differential equations but have no solutions. That's what I say. So mathematicians, okay, you have no solution. I give you the this kind of solution, this kind of power series. All right. So all the differential equations is solved by a power series. Because they solved by power series, they find out that power series is this kind of form. And then they define this form as exponential function. That's it. That's true. It's nothing funny on that. Think about this. You ever get any exact solutions? No. You're supposed to have go to infinite to get solutions. How can a computer get infinite terms? None. So, exponential function is nothing but an approximate function. It's a function to represent a power series like this. And they call this is exponential functions. So mathematician is very smart. They fool everybody. This is a power series. That's not the real functions. It's a power series. Sine, cosine is all the same thing. It's just a power series. So you can name it Bessel functions, elliptic functions, all the functions is nothing but all just power series. Agree? So realistically, there's no differential equation has closed-form analytical solutions. That's what I say. They're all just involved in the power series, the solutions. This is why I show you this curve. I'm saying if n larger than 6 or 7 or 8, that's close enough. At least from engineering point of view, that's close enough, right? N is the term. How many you use? N equal to 0, that's this term. N equal to 1, n equal to 1, that's this term. N equal to 2, and so on. 1 term, 2 terms, 3 terms, 4 terms, 5 terms. It's k. Well, no, k equal to 0 to infinity. So that's k from 0 to n here. I just assume that the not in infinite is n here. Assume n is here. If n going to infinite, then it's become et. If n is a fixed term, there's n here. Understand? Okay. So you can see that if n is increasing, then it's n up to about 8 is close to exact, but this is not really exact. That blue line is not really exact too. That's just up to your machine accuracy. Then put this way. You have a 32-bit, you have one curve, you have 64-bit, you have another curve, but your eyes cannot see the differences. The computer will. Now you understand, right? Okay. So that's just for our eyes. But that's good enough for engineering applications. That's all. Okay. Matter of fact, This kind of function, log functions, E functions, those are just power series expansions. Same thing. And mathematically, you can write like this too. E t equal to 1 plus t over k and the k to the power when k go into infinite. So you can all kind of different form to represent this power series. But your computer, when you ask your computer to compute ET for you, they do this way. Really, I'm not joking. That's the way they give you the value. All right. Now, give you some mathematical background here, then you will know how to solve the homogeneous equation here, the homogeneous solutions. So this is what I call y equal to E gamma t. Keep in mind, not just a power series. Keep in mind. And we sub there, as a matter of fact, originally, mathematicians they really insert the power series expansion into this differential equation, and then they solve it. That's true too. And then after that, they define that's exponential functions. Then you find the characteristic equation, right? This is all your mathematics, your engineering mathematics textbooks already show you. I don't want to repeat those, but I want to tell you characteristics equations and the roots. Now we have to look at the roots. I want to see the roots. I want to explain the roots. What does that roots mean? Gamma 1, gamma 2, gamma n. That means the eigenvalue of the system. Okay? So that gamma 1, gamma 2, gamma 3, and so on give you the frequencies and damping information in there. Your engineering mathematics will tell you that's just the roots. They don't tell you what does that mean. Because of that roots. They give you the solution of like this. That's the solutions. Agree? Are you sure? Is that really true? Well, sometimes you got a question to your teachers, you know. Do you think that's always true? Think so? Agree? Is there any condition on this? Huh? No? Huh? Well, that's, we assume gamma 1, gamma 2, gamma to gamma n, or what? Or distinguished or not? You forgot about your engineering math now, right?
The way you put frame system,
no?
confused.
Huh?
Oh, sure, there are conditions.
Well, if you can write them this way, right? But if you gamma 1 happen to be equal to gamma 2, then what happens? Are you sure this solution is always true? If they are all distinguished, yes, they're just true. If they are not, then not. So, if gamma 1 equal to gamma 2 equal to 0, that's just like a rich body. This is not true either. All right. We are again. I keep saying that we are not talking about math. We are talking about our system here. What do we mean? Gamma 1, gamma 2, gamma 3. Those again, I just tell you that those are the eigenvalues of the system, and that give you the all the information of the frequencies that damping. All right, now That's why I ask you the last slide. They always get some conditions. So now I'm telling you some condition for that. Real long repeated eigenvalues. I say real long repeated eigenvalues. And that is like that. I say real. I'm not talking about complex. All the eigenvalue are real. What does that mean? I already told you. That means you have only damping, you don't have frequencies. True? So think about that. So when you look at the roots, think about those are eigenvalues. If those eigenvalues are real, it's not complex, no imaginary part, that means no frequencies. Okay? That's the message I want to give to you. Yeah. Example. All real part has roots, -1 and -2. All right. That's the solutions. Again, there's no imaginary part of the roots. So if you think about this, if I have a system like that, and I have no frequencies involved in there, I just got the damping. And I believe you can solve this mathematically. And this is the C E minus T, this E minus 2T. That's the curve. You have initial, for example, you have initial displacement like that. Then it just decay quickly in 6 seconds. You don't see any oscillations, did you? No, because you have no frequencies. The question is, can this system, we go back here? We go back here? Oh, wait a second. Well, let me just, I don't want to go back because that's maybe too far away from here. Okay. Now now we need to think about it. Can I design a tuned mass damper that I have no frequencies involved there? That's the question. I have a spring, I have that spot, but I don't find any frequencies here. Is this possible? Is this possible like that? Ah, that's right. So in this class we'll discuss about that possibility. All right. So the damping, the tuned mass damper, can I design a tuned mass damper that I don't have the pure imaginary part of the system eigenvalues? That's we'll answer that later. Okay. Now the compressed root. The compressed root of this, gamma squared plus gamma plus 1 equal to 0. And this, again, is like a spring and despot system. The third motion I introduced to you and has having two roots. Gamma 1 equal to minus half plus I square root 3 divided by 2. Gamma 2 equals to half minus I square root of 3 over 2. All right. Now this is complex conjugating. why eigenvalue always come with a pair of complex conjugate? That's the question I have. Anybody knows the answer? Is there any possibility for a two eigenvalue system like this? I have one complex, one real. Tell me. Anybody knows the answers? Yes or no?
乘起来会有复数。
Let me say, anybody think any system, you don't have to be like this, any second order system like this. Is it possible to have the one real root, one complex root? What your engineering mathematics teacher didn't tell you that? No? Or the textbook didn't write it down? Think about that. All right? The answer is it always comes with a pair. Why? Because the coefficients of this are real. The coefficient of any differential equations, if they are all real, they always come with complex conjugate. Otherwise, you won't get back to real differential equation like this. All right? Understand? So if somebody solve a differential equations, the second order one, and real coefficients, and then they got one real, one complex, then I will say that's something wrong in that solutions. If there is nothing wrong on that solution, that guy can get Nobel Prize. All right, that's a new math. Because that doesn't meet the real system, the physics. Okay, now we have a real part, we have imaginary part. In our mechanical system means this imaginary part gives you the frequencies. The real part gives you the damping. So the damping of these two roots are the same, but frequencies, they have phase different. That's true because one is associated with displacement. Another one is associated with the velocities. The displacement and velocities, their phase always different. Okay?
I think I've experienced a case whereby maybe for a 3rd degree,
Yeah.
you have one rail and then the other two will be
complex conjugate.
Right. So
as long as you get a complex, you have a complex can come out. Okay. So 3, you have one real, 2 complex conjugate pair. You cannot have 3 complex eigenvalues. One must be real. Or 3, order 3. Now, this is the general solution you can write in terms of cosine, sine, or you can write in terms of this. And if you look at this, you have the this is the real part come out from here. Your imaginary part will become a cosine and sine combinations. That's how the frequencies come out. All right. So you have cosine and sine, that means you have oscillations. The real part won't give you sine or cosine. No. Okay? Only imaginary part will give you cosine and sine. And that cosine and sine, those square root 3 divided by 2 means the frequencies. Okay. Now, you can see the oscillation here. Although it damped up quickly, this doing like this doing like that, they do have damping there. But they also have oscillations. But because of this, give you the quick dampings, so your oscillation won't go too far and it's gone. But you can see that they try to oscillate. They try to oscillate, but because your distance kill them out. So most of TMD will be looked like this. When you design TMD like this. All right. If you can design a TMD like this, you'll be happy. Your oscillation is minimum. And let's take 10 minutes break now. It's more than 7 now. All right.